Hello, everyone, and welcome back for another installment of AP Physics 1 Prep. My name is Dave, and I've been with you for a few sessions now. This is session 3 of 3. In the first couple sessions, you might recall if you were around for it or saw the recordings, that in session 1, we went over general test structures. We also talked about some general test strategies for the kinds of question types you'll see. And we touched a little bit of on a little bit of the content when it comes to kinematics. We talked about some definitions there. In our second session, we spent our time on content, where we focused on uh, uniform accelerated motion for kinematics. We talked about dynamics, so getting into forces and Newton's laws, and we also talked about circular motion and gravitation. So if you missed those sessions and you want to hear what we talked about there, you can check out the recordings of those sessions that can be found on our Princeton Review YouTube site. For today's session, we're going to round out the conversation on the content. We're going to explore themes in energy and conservation of energy. We're going to talk about momentum and conservation of momentum. We're also going to explore simple harmonic motion and torque and rotational motion, and that'll take us through our review series. So getting right to it, let's go up to our conversation on energy, and that actually starts with this quantity called work. And what work represents for us is a scalar way of trying to explore the motion of objects. And what it gives us is the contribution a force offers to an object's motion, so its displacement and speed. And we see that reflected in the equation for work down here. So work is equal to the magnitude of a force of interest onto a magnitude of displacement experienced onto cosine of the angle between those two. So let's make a note here that we've got units of capital J for joules when it comes to this quantity of work. And this work is a scalar quantity, but it can be positive or negative or zero. And the different signs you get for work are really coming from this cosine theta term. After all, F and D, these are magnitudes of those vectors. So they're going to be non-negative. So the sign on W comes from cosine of theta. So for instance, looking at the figure above, if this is our force of interest, which makes this acute angle with our displacement shown here to the right, well, then cosine would be some positive quantity and the work done would be positive. Physically, what this means is our force of interest has some sort of component or a piece that goes with the motion. And so that's positive work. If we considered a different force, like say kinetic friction, which is always directed opposite to the motion, well, here we would end up with cosine of 180 degrees, which would be -1. And so the work there would be negative now. But again, physically, this does represent the fact that our force has some component, in this case, the whole thing, that goes against the motion. And if we consider other forces that are present in the problem, like say the normal force from the surface below, the weight it would experience, those forces are vertical. So they're perpendicular to that horizontal displacement. So there we'd end up with cosine of 90 degrees, which gets us 0 work done. And what this tells us is these forces don't have a component with the motion for positive work, and they also don't have a component against the motion for negative work. So 0 work done in that case. So let's go to an example to see how we might be tested on work and how we might calculate values of work. So in this example, it says a 15 kilogram crate is moved along a horizontal floor by a warehouse worker who's pulling on it with a rope that makes a 30-degree angle with the horizontal. The tension in the rope is 69 newtons, and the crate slides a distance of 10 meters. Our question asks how much work is done on the crate by the worker. So what we can see in the question are a few things that make us think about forces, right? Pulling, rope, tension, even work that we're asked to find. We know that can be defined in terms of work, like we just saw on the previous slide. And when it comes to that can be defined in terms of force, I should say, like we saw on the previous slide. And when it comes to dealing with forces, having a diagram can be very useful to make sure we get all the right forces. We know what terms are referring to what. We get the angles correct and so forth. So just a quick sketch of what's happening here. There's some sort of mass. It is displacing to the right, and there is a force that's known to us, and this force is acted at a known angle from the horizontal and hence from that direction of displacement. So when it comes to finding the work done by that tension force, we would take the tension force multiply by the magnitude of that displacement, and then cosine of that angle, which is 30 degrees. So plugging in the values, we've got a number for the tension, a number for the displacement. Cosine of 30 we might know is root 3 over 2. Of course, you've got a calculator to work through all of this. And when we work this out, what we'll find is our work is about 600 joules. And that's how we can calculate this value of work. I should point out now while I think about it, if we have questions at any point, as we're going through examples or talking about different concepts or what have you, feel free to ask. Marcy, who's in your chat room with you, will relay your questions to me here in my classroom, and I'll do my best to address whatever questions you have. So this is work, but the unit is called energy, right? So now there's this question, okay, well, how do these different pieces relate, right? And so the thing about energy is defined as the ability to do work. So if an object can do work, then we say it must possess this quantity of energy. And one way that an object could do work is by virtue of the fact that it's moving. So if you thought about, say, like a hammer moving toward the nail, when it contacts the nail, through that contact, it can deliver a force, which then could cause the nail to displace like into a wall. But there you get force and displacement together for some sort of positive work done. And again, that was owing to the motion of the hammer, right? So that kind of energy associated with motion is what we call kinetic energy. So kinetic energy is the scalar quantity that we see right here. It's found by taking half the mass onto the square of the speed. And so if you plugged in the units here, you would end up finding those same units of joules that we had for work. And in a way, this makes a bit of sense because we are saying that energy is the ability to do work, right? So conceptually, they're very intimately tied together. Um, and so it would stand to reason then that they would share those same units. They should be similar in that regard. But it also stands to reason that there should be some sort of a quantitative relationship, like an equation to link these things together, the idea of work and this kind of energy. And we see that captured here in what we call the work kinetic energy theorem. So this tells us that the total work done is equal to the change in kinetic energy experienced. So let's explore some of those ideas by working through this example. And the example asks, what is the kinetic energy of a ball with a known mass moving with a speed of 30 meters per second? Well, this is essentially testing, do we know the equation for kinetic energy? So we can jot the equation down and plug in the pieces and work out the math. So we've got the mass of 0.1 kilograms, speed is 30 meters per second, which we can square. Again, there's a calculator on the test, right? But thinking about this in mental math, 30 squared would get us 900. 0.1 is a tenth. 900 divided by 10 gets us 90. And cutting that in half would find 45 joules of kinetic energy. So straightforward plug and chug, but let's take the question a step further. Let's do a follow-up example with this. And I'll type this in for you folks. Let's say if the object starts from rest, the question we can ask is, what is the network done? So why don't I ask you folks a question? You can, and someone can chime in and let me know. If an object starts from rest, what's its speed at that moment? If an object starts from rest, you can type into your chat what we think that initial speed would be, and then Marcy can relay that back to me. No answers coming in just yet. So I'm asking the question because it really helps us quickly sift through what we're about to do with the problem. So let's set up the problem a little bit first. Our question here is, what is the network done? And so when it comes to finding that network, we might be thinking more about what we just brought up a moment ago, where work could be force onto displacement and cosine of an angle involved. But we don't have that kind of information here. Instead, what we have are these other scalar quantities, right? Mass, speed. So instead of focusing on like force and displacement, which were vectors, now let's think about work in terms of the scalars, which brings us back here. So we can claim the network done. Okay, perfect, Rahul. Yeah, it's going to be a 0, right? So the network done looks like the change in kinetic energy. Change in anything is the final value minus the initial value. But notice if we start from rest, and like Rahul said, that means there's 0 for the speed. Well, that would also mean there's 0 for the kinetic energy. So that initial kinetic energy is going to be 0. And what we're left concluding then is the network will look like what that final kinetic energy is. And so the network is also 45 joules. So we have a few ways of finding work, right? We can deal with the forces and the displacement if we happen to have those vectors handy, but otherwise we can look at scalar quantities and turn to this work kinetic energy theorem for a bit of help. All right, so in this conversation, we talked about one kind of energy, right? This kinetic energy, but it is only one kind, right? There are multiple forms of energy. Another example we could think of is, holding up a hammer, right? And then letting go. And what the hammer will do is fall, right? We know that from everyday experience. But what happens there is by virtue of having that initial position, the hammer could fall when we let go, right? And then it gains kinetic energy, which we, as we're seeing here, can have that turned into work done. So maybe the hammer hits a nail and displaces it into the floorboard, right? But it's all by virtue of having that initial position that the hammer could now do work. And so we have a new form of energy called potential energy, which is the energy of position. And in the case of that hammer, this potential energy is owing to the presence of gravity, right? It's the gravity that gets the hammer to fall and ultimately ends up doing work. So we've got gravitational potential energy in particular, and seeing what's happening here, right? We had the potential energy at the start be converted to kinetic energy, which gets transferred into work done. So, sort of connecting those pieces, then the change in kinetic energy should kind of look like the work done by this particular force. And so, what we're able to claim then is the change in gravitational potential energy should look like m times g times that change in height, right? Because notice this would be force, right? With gravity, that's mg, onto the displacement, which is that height through which the object falls, right? Or instead of looking at the change in gravitational potential energy, we might instead focus on the gravitational potential energy at individual heights. Right, there's a few ways to try to set up the problem, and we'll see that when we look at energy conservation, which is really where we go next. Because if we do have this trade-off, right, potential energy turns into kinetic, or maybe kinetic and then turn back into potential, but the total stays the same, then we really do have like energy conservation, right? The total is constant. And we can know that that's going to be true so long as the forces that are present are what we call conservative, which for this test basically means a gravity force or a spring force. If you only have one or maybe both of those present, energy is conserved. And that's what we're showing on this slide. So the total energy is not too different from total anything else, right? Like total force, add up all the forces. Total work, add up all the works. Total energy, add up all the energies. So here, if we account for the kinetic energy and the potential energy the object has, that should sum to this fixed value that doesn't change over time, which tells us then we could say the sum of the energies to start should look like the sum of the energies at some later time, right? And that's your energy conservation. So let's go to an example to see how we might have that tested. So with example 13, this says a ball of mass 2 kilograms is gently pushed off the edge of a tabletop. And this is our way of just trying to convey that the initial speed is basically 0, right? So it's allowed to fall, but It's basically falling with, a negligible initial speed, right? And the tabletop is 5 meters above the floor, so pretty high up. But the question asks for the speed of the ball as it strikes the floor. So we want that impact speed. So this question, this concept, right, conservation of energy, isn't too different than like a kinematics question or Newton's second law of force-based problem, in that a diagram can be very helpful to give you context and visualize what's happening. So let's do a quick sketch of what's happening here. So here we have a known mass, and it's released from rest. We're interested in that final speed, and we know the height that this is dropped from, which is that 5 meters. So the only force present here is going to be gravity, right? This is basically a free fall problem, and if gravity is the only force present, energy is conserved. So we can set up the problem using what we saw in the previous slide. We are covering topics in momentum, Luke. Yes, we'll get to that actually pretty shortly. So setting up conservation of energy, we're saying the initial energy should balance with the final energy. And some of these terms can disappear for us, right? Because again, if there's no speed to start, well, then there's no kinetic energy to start. So that's going to vanish for us. And when it comes to these heights or these positions in general, you can choose where position 0 is. So if we make the ground our height 0, then notice that's our final height. So the final potential energy would also be 0. And this brings us to this very sort of classic kind of a problem where potential energy is being fully converted into kinetic energy. So let's re-express these terms. We can say the initial potential energy is mg times initial height, and the final kinetic energy is 1/2 mv final squared. So at this point, we've got numbers and we can plug them in. But like I said back in our first session, you should rearrange and isolate what you're looking for first before you put in numbers. Because notice here, like we know the mass, and we could plug that in here and crunch a number with it. We could plug that in here and try to simplify the right-hand side of it potentially. But why deal with all that extra math and make the numbers all the bigger? Because notice if mass is found on both sides, we could divide through by mass and cancel it out. That would leave us with just g height initial is 1/2 v final squared. And then to isolate for v final, we could multiply both sides by 2, take a square root on both sides, and now we can plug in our numbers. So little g, if you can recall, that's 10 meters per second squared. And for the initial height, that's 5 meters above the ground. 2 times 10 is 20, times 5 would get us 100. And the square root of 100 is going to be 10, and we've got SI units here, so meters per second for this speed. And so that's our conversation here for work and energy, and in particular conservation of energy. Very powerful tool for handling a lot of different problems. What we will switch to now is what Luke was asking about, which was concepts in momentum. So momentum is a vector quantity now. So with energy and work, we were dealing with scalars. Now we're back into vectors, which means we have to be very careful with our signs and very careful with our directions. And we might be back into that world of components now. But momentum is given by p vector, and it's the scalar mass times the velocity. So there's the vector on the right-hand side. And notice what this momentum really puts together for us is an object's motion, the velocity it has, with its resistance to changes in motion, that inertia or that mass. And when we say things like state of motion and resistance to change in the state of motion, that should make us think about forces in Newton's laws. So it's no surprise then that momentum is something that we can relate to force. And we see that here. What we see as a force is really a change in momentum per change in time. And looking at these different expressions, here's what we can claim about the units. Momentum would have units of mass onto speed. So that would be kilograms meters per second, or like we see here, momentum should look like force times time, in which case we could also claim units of newtons seconds. So a few equivalent sets of units, and it's good to be clear on both of those. So how momentum is often used on the AP Physics 1 test is with conservation of momentum. So here we make the note that conservation of momentum can be employed if our system is essentially isolated. So if there are some sort of external influences on the system, that they are somehow balanced out, right? So if there's no net external force on your system, then momentum will be conserved. And what that means is whatever initial momentum your system has, that should balance with the final momentum of your system. So to be clear, that total momentum means you need to add up all of the momenta of all the different masses that make up your system, right? And what you find in an initial state should balance with a later state. So let's make a note of when we often turn to this for help. So this is often used with collisions, explosions, recoil, and radioactive decay. So we don't need to know about nuclear physics for this test, but if you did have a question that starts talking about things like radioactive decay, you should immediately start thinking about something about conservation of momentum here, right? But collisions, this is where we most commonly see momentum being tested in AP Physics 1, and in a moment we'll see why we turn to conservation of energy to work those kinds of problems. So for collisions, we have three types, and we're discussing them here on this slide. An elastic collision, kind of like the name is implying, suggests that there's a lot of rebound. Um, and in these cases, what you have is momentum being conserved. So you could use conservation of momentum to help solve for unknowns. But kinetic energy is also conserved for these kinds of collisions. A different kind of collision is an inelastic collision. And you break up that word in inelastic, and what it's telling you is it's not elastic, right? So you don't have that sort of perfect rebound that you had before. So here momentum is still conserved, but kinetic energy is not conserved. So some kinetic energy will be lost. And that makes a little bit of sense because in any collision, there's all kinds of ways for energy to leave your system, right? Like the two objects that collide, they might end up rubbing up against each other, and that can generate friction, which takes energy out of the system, often in the form of heat. When two objects collide, and I'm not sure how well you'll hear this, but when two objects collide, they make a sound, and that takes energy out of the system. And when objects collide, they might deform somehow, like pool balls dimpling, the bumpers of cars crumpling a little bit, and that takes energy as well. I have a question here. It says, at some point, could I explain which equations we should remember because they're right. So you do get a little equation sheet on the test, and they will give you some of the equations that you're going to need, and they can be useful, right? In terms of what equations you want to know, I mean, the best thing to do is to see, well, what's commonly tested. So there's a few ways to figure that out. One thing you could do is you could look through College Board's AP Physics 1 website, where they have a bank of past exams where you can see the equation sheets that went with those tests, as well as the past questions that were asked and what equations were used. So very valuable resource there. You could also check out the Princeton Review's AP Physics 1 prep book, which contains the content you need to know for the test, as well as a summary of the most used and tested equations. But I won't have like a sort of a synopsis of what equations to look at. If you wanted a bit of a snapshot on what is commonly used, aside from getting to the practice, looking through the past exams, and various prep materials like this as an example from the Princeton Review, then you could take a look back at the previous review sessions and pair that with this one to see the kinds of equations that are commonly used. So I hope that helps to address your question. And then aside from the inelastic collision, we have a perfectly inelastic collision. And like this phrasing of perfectly implies there is absolutely no rebound whatsoever, which means the objects collide and they stick together now and move off as one. So here, momentum is still conserved, but kinetic energy is not. And in fact, here you get the greatest loss of kinetic energy. But what we can see in all cases is momentum is conserved. So it's a very handy tool to use in these collisions problems. So let's go to an example to see how we would work that. So in example 6, it says two balls roll toward each other. The red one has a mass that's known and travels with a known speed before the impact. The green ball has a known mass and a known speed as well. And looking at these masses and speeds, can anyone tell me which of these objects is going to win out, right? When they collide, is it the red one or the green one? Right? Think about how the masses and the speeds compare. Which one of these masses is going to win in the collision, right? Does the red one win out over the green one, or does the green one win out over the red one? It's little predictions like this that can help us with process of elimination, for instance, with multiple choice questions, because any answer choice that goes against what we would anticipate from knowing the physics, we could eliminate outright and avoid trap answers potentially. And it's a good way to assess our results when doing those free response questions. So does anyone have an opinion which of these objects will win out? You can let us know in the chat, and Marcy will relay that back to me. Is the red ball going to win out in this collision, or our green ball? So Rahul says red, and Rahul, you're right on. Right, so you've got a more massive and a fast-moving object. Greater momentum says this one is going to win out. So when working the problem, it helps when we see a collision, and that's our red flag, to think about conservation of momentum, to try sketching out the scenario before and after the collision. So here we get some insights into what things look like before. So let's draw that out. We've got the red ball with a certain mass, traveling with a certain speed. Heading towards it is the green ball, traveling with its speed. After the collision, what we're told is the red ball continues forward as we're anticipating with that known speed of 2 meters per second. But we're also expecting now that this green ball should be bullied, right? Like the green ball isn't going to somehow pass through the red ball. Instead, it'll get pushed back the way it came. So then what the question first asks us is, what is that speed of the green ball after the collision? So we want to think about conservation of momentum because we have a collision. But like I said before, we're now dealing with vectors. So we have to be very careful with our signs and our directions. So let's choose a direction to be the positive direction, say to the right, based on the figure I've drawn, which is basically like saying, let's make the direction the red ball travels in initially to be the positive direction. And what we'll claim is initial momentum should balance with final momentum. In the initial case, we have momentum for the red and the green ball to add in. So we'll have mv for the red ball initially. We'll have mv for the green ball initially. But notice here, if the red ball is traveling in our positive sense, well, then this is a positive quantity. But if the green ball is traveling to the left, which is our negative sense, then that's a negative quantity. And that should balance with what we find afterward, which there's momentum for the red ball and momentum for the green ball, and these should both be in the positive sense. So what we need to find is this final momentum of the green ball, or sorry, this final speed rather, of the green ball. So let's isolate for that. And we can do that by taking this term and bringing it to the other side. And then after that, we can divide through by the mass of the green ball. And now that we've isolated for what we're looking for, we can plug in numbers. So we've got a mass for the red ball and an initial speed, a mass for the green ball and an initial speed, and then the red ball has a known final speed. So working the mental math, half of 4 is 2, half of 2 is 1, and we need to subtract that off. So that leaves us with 1, and then we're subtracting an extra 0.4. So that would get us 0.6. We're still dividing by 0.2, which looks like 6 divided by 2, which is 3. And everything here is in SI units, so meters per second. So that final speed of our green ball after the collision is 3 meters per second, and to the right in that positive sense. The follow-up question, though, asks us, was the collision elastic? And what this is essentially testing for us is, do we know what makes elastic collisions different? And what that is the fact that kinetic energy is conserved in the elastic case. So if we want to assess whether or not this collision was elastic or not, we should compare the kinetic energies. So in the initial case, there was kinetic energy from the red ball and from the green ball. Those numbers are in the question itself, so we can plug in with the values they gave us. So 4 squared is 16, cut in half is 8, cut in half is 4. And then 2 squared is 4, times 0.2 gets us 0.8. Cut in half is another 0.4 to add on. And everything is in SI units, so that would be in joules. For the final kinetic energy, again, both masses have that kinetic energy, so we'll have to account for that. And here we'll make use of what we just found for the green mass's final speed. But we can plug in the numbers. And here's what we find this time around. 2 squared is 4, cut in half is 2, cut in half is 1. 3 squared is 9, times 0.2 is 1.8. Cut in half is 0.9, which we add on. And so here's what we notice. The initial kinetic energy does not match the final kinetic energy. So the conclusion then is this collision is not elastic. In terms of what kind of a collision it actually is, well, notice that it's not elastic because kinetic energies don't match, but it's also not perfectly inelastic because recall in that case, the two objects had to stick together and move as one. But that's not going to happen here because the red ball travels with 2 meters per second, but this green ball travels at 3 meters per second. So they're pulling away from each other, kind of thing, right? So instead, this is just the inelastic case. So this is what I wanted to cover for momentum and conservation of momentum. What we're going to have to switch to next is simple harmonic motion. So with simple harmonic motion, here's what we have. There's going to be movement that is repeating or back and forth. And that's fairly straightforward to tease out of the language here. But the simple part is actually not so straightforward. That label of simple for the harmonic motion tells us that quantities called frequency and period are independent of the amplitude. So these are terms I'll define shortly, frequency, period, and amplitude. But this notion, this concept is one that I wouldn't be too surprised to see tested in a multiple choice problem, or maybe even as like one part of a free response question. So it's a good thing to keep in mind. But for simple harmonic motion, what you have is some sort of an object, like I said, it's going back and forth, right? It's continuously going to where it was before. And a common system to look at to explore these concepts is a spring mass system. So if we had a spring and we attached a mass to it, it would just sit there. So this is what we call the rest position or the equilibrium position. But if we gave that mass some energy, like maybe we hit it, then it could move. And what that could then do is cause the spring to get stretched, but the spring is going to resist that stretch, and it's going to pull back on the mass and say knock it off. So the mass is going to slow down the entire time it's heading to the right and eventually stop. And at this maximum displacement from equilibrium, the mass will have achieved its amplitude. But the spring will continue to pull the mass back to where it was before because the spring wants its natural length. So the mass ends up being accelerated on the way back to the rest position. So when it finally gets there and the spring is happy, well, the mass has actually built up all this speed that's going to carry it through the rest position, which now causes the spring to get compressed. So now the spring pushes back the other way on the mass to slow it down and have it stop at an amplitude now on the other side of the rest position, and then continues to push and accelerate the mass back the way it came. So when the mass gets back to the rest position, it'll have built up some speed. That's going to cause it to move through the rest position and stretch the spring, and thus the whole process repeats. So simple harmonic motion. But notice what we're showing here, going from panel 1 down to panel 5 is one full cycle or a full oscillation, which would have your object return to where it started, but also have the same sense of motion. That's a full cycle. So in these cases, then, there is this force that when the object displaces one way, the force opposes that. So this restoring force that brings the mass back to where it was before should have some dependence on displacement. And for the spring mass system, we see that reflected in what's called Hooke's law. So this expression here shows us that this spring force is proportional to the displacement and oppositely directed to it. So that K is called the spring constant or the force constant or the restoring constant. It's got a few names. And it has units of force per displacement, so newtons per meter. So a question we can take a look at that uses this, but also has a few hooks involved, and I do, pardon the pun there, is the case we have here. So this example says a 12 centimeter long spring has a force constant K of 400 newtons per meter. And the question we're asked is how much force is required to stretch the spring to a length of 14 centimeters. Well, they bring up a spring constant. We've got forces involved. So this is all going to be about Hooke's law. So the magnitude of that force looks like the spring constant onto the magnitude of the displacement. So the first thing we have to be careful with is what to do for the displacement. So can anyone tell me what is the displacement? What value do I plug in for x here? They tell us the spring starts out 12 centimeters long. It finishes 14 centimeters long. So you folks let me know, what number should I use for x in this case? And this is that first hook to be careful with, right? We see these different lengths. It's probably easy, especially if we're concerned with time, to just shove one of these numbers in and assume that that's correct, but that's not quite what we need to do. Yes, exactly, right. If this is the rest length and this is our new length, well, the displacement or the extra stretch we're given is the difference. Yeah, exactly. So it's 2 centimeters. So that's the first thing to watch out for as a hook. The second thing is the units, right? Which you can always be clear on based on the answer choices that are present. But, if we've got newtons per meter for K, well, then we probably want meters for the displacement as well. Yeah, so we don't want to use 0.12, right? Because this is just that rest length, right? So the stretch involved is that displacement away from that, right? That change away from the rest position. So that's the extra 2 centimeters gained. So we'll use 2 centimeters or 0.02 meters. That'll be our x value. Perfect, Luke. So multiplying those two together, what we would end up finding is the spring force would be 8 newtons. All right, so this is a little look at that specific force for a more technical kind of number crunching question, but you also get questions that are a bit more conceptual, just asking you about what's true about your oscillator or your mass um, at specific interesting points in the motion, particularly at either amplitude, like we're showing in this figure, or the rest position. So, and again, we've got the definition of amplitude here, right? Which is that magnitude of the maximum displacement um, from equilibrium. So at either amplitude, where we have that max displacement, recall that our spring force as a magnitude is k times x. So if we max out the displacement at the amplitude, we'll also max out this restoring force, which is why we have the note here that spring force is a maximum at the amplitudes. We also make a similar claim about acceleration. So can anyone remind me, how do we relate force to acceleration? What was that famous equation that Newton gave us that went along with Newton's second law? Because this will help justify the claims we have here about how acceleration is maximized, which might not be the most obvious statement. So I need that equation for force that goes with Newton's second law that relates force to acceleration. F net is ma, that's exactly it. So notice if the uh, displacement is maximized and hence the force is maximized, and that's the only force present, that is your net force. So that's maximized, meaning your acceleration is maximized. So that's why we have the claims that we've listed here. And of course, at the equilibrium position, if there's zero displacement, there's zero spring force, and no force means no acceleration. So it's good to know these properties at these different points because, like I said, AP Physics 1 exam tends to ask some conceptual questions about this stuff, particularly in multiple choice problems. But it turns out that this spring force, much like gravity, is a conservative force, meaning that it too has a form of potential energy. And the potential energy for a spring is equal to half the spring constant onto the square of the displacement. So with that in mind, if I look at these same interesting points in the motion, but now I look at some scalar quantities as opposed to the vectors like force and acceleration we just looked at, here's what I can claim. When position is maximized or that displacement is maximized, so would the potential energy be maximized, which is why potential energy is a maximum at either amplitude. But remember, at the amplitude, that's where your mass would stop and then turn around and go back the other way. So the speed would be zero at those points, which means the kinetic energy would be zero at those points too. And then through the rest position, you've got zero displacement for no potential energy, but it's through the rest position that the object has its max speed, right? It's been accelerated on the way back to the rest position, and the moment it overshoots it, the spring causes it to slow down again, right? So if the speed is a max at the rest position, then so is the kinetic energy a max at the rest position. And like I said, this is a conservative force, a spring force, so energy is conserved. So notice at the amplitude, that constant energy is equal to this max potential energy, but in the rest position, that constant energy is just the max kinetic energy. So as a quantity of energy, the max kinetic and the max potential energies should be the same, which is an interesting fact we'll make use of in the next example. So this question says a block of mass 0.05 kilograms oscillates on a spring whose force constant is known. The amplitude is also known. And here we want the max speed of the block. So in terms of setting up the problem, notice the question's asking you for speed, which is a scalar. And what they give you is mass, which is scalar, spring constant, which is scalar, and amplitude, which is scalar. So we should be thinking about scalars, which makes us think of energy considerations. And when they bring up maximum speed, this makes me think of max kinetic energy, which, as I just noted, is the same amount of energy as that max potential energy. So let's explore where this leads. Here we can say 1/2 mv max squared, and that's equal to 1/2 k max displacement, so that'd be the amplitude squared. Can multiply both sides by 2 to get rid of the halves. And to get V max alone, we could divide both sides by the mass and then take a square root on both sides. And just to show you an equation that's actually um, something good to bring into the test with you, let's notice that underneath the root, we've got a certain product. Well, instead of the root of this product, let's write that out as a product of roots. So here we claim V max is root k over m onto root of a squared, which is just a. And this little equation is one that's nice to have in your back pocket. That way you don't have to worry about, thinking how to set up the problem to derive the expression, which you then ultimately use. It's pretty common to have to work with this. So the max speed of your spring mass oscillator is root k over m onto a, the amplitude. So in this instance, we'll plug in our numbers. K here is 500. The mass is 0.05. The amplitude is 4 centimeters. And again, putting that into meters, we get 0.04 meters. Working out what's under the root here, that would end up being 10,000. Again, you've got a calculator, but you could work that out potentially with a bit of mental math. And then the root of 10,000 is 100. And applying that to 0.04 gets us our final answer. Vmax is 4 with those SI units of meters per second. But notice how much quicker the problem would be if we had this equation already to go, right? It's asking for max speed. So it brings me into this equation, and they give me mk and a, right? And there's mk and a, right? So this brings us through much of what we need for the spring mass systems and oscillations in general for some concepts. But there are a couple of terms we still need to define, and that is period and frequency. So period is the time required for a cycle or an oscillation. So however many seconds occurs for that oscillation. A frequency, on the other hand, is telling you how many cycles that occur in a given time frame. So let's note for frequency, then we'd have units of per second or inverse seconds, which we call Hz for hertz. So if you see that Hz, that's what it's referencing, per second or hertz. And when we think about those units, right, seconds per cycle versus cycles per second, we really see that period and frequency are reciprocals of each other, right? Period is a reciprocal of frequency, and hence frequency is a reciprocal of period. And it turns out that each simple harmonic motion system has its own unique equation for period and frequency. Um, it, it, if you take a look at the past exam equation sheets you get, you'll see the period for a simple pendulum and the period for a spring mass system are included. And we can see those, or one of those, on this slide here. So the period for a spring mass system is 2 pi times the root of the mass over the spring constant k. And because frequency, recall, is 1 over period, the equation for frequency looks like the flip of all this. So instead of 2 pi, you get 1 over 2 pi. And instead of root m over k, you get root k over m, right? So with example 7, they give us a mass, they give us a spring constant, and they ask for the frequency and the period. So taking that equation for period, which again I would anticipate is on your equation sheet on the exam, we can write in 2 pi root m over k. Plug in those numbers they gave us, 2 for the mass, 300 for k. And then turn that out with a calculator, right? Get 0.51 seconds. And we might be tempted when it comes to solving for the frequency to set this equation up and plug numbers into this and plug all that into the calculator to solve. But A more straightforward way of getting at your answer is, again, to realize that frequency is a reciprocal of period. So just do 1 over the 0.51 you just found to get a frequency of 1.9 hertz. A bit more direct. And that takes me through what I wanted to cover for simple harmonic motion and oscillations, which means now in the time we have remaining in the session, we'll say a few words about torque and rotation. So with rotational motion, there's a lot of similarities to what we just did in the last 2 sessions with linear or translational motion. So if we have uniformly accelerated motion that happens to be rotational, um, we can use the big five to explore what happens there, right? So here's your big five that we saw in session 2, right? For linear motion, whether that's, left, right, or up, down, whatever it is. But now if we have rotational motion, where, the motion is, like clockwise versus counterclockwise, it's a very, very similar set of equations to work with. So instead of the displacement being, say, like the change in an x coordinate, the displacement now is more like what angle did you sweep out as you were, going through a certain turn. So delta theta for the displacement. We'll use omegas for the velocities and alpha for the rotational acceleration. So same equations, we're just swapping out the variables with these, curvier Greek letters to denote that curvy rotational motion. And when it comes to having a change in motion, like being stationary to then rotating, right? What Newton gave us was that there should be a force responsible for that change in motion. And that's true here with rotation. But when it comes to rotation, there's more than just the force to consider. There's also how the force is applied, where it's applied, right? That kind of geometry is relevant. And we see that captured in our expression here for torque, where torque is our measure of how effective a force will be at causing rotation. So torque is equal to r here is the magnitude of a vector that I'll draw in a moment. Onto F, the magnitude of the force of interest, and then theta is the angle between those two vectors. So again, to clarify what those different vectors are, let's consider a bird's eye view of a door, right? So here's that thin slab of the door you might see as you're looking down on it from above. And here is maybe the hinge where the door is hooked up to the wall. And sometimes that hinge is called a pivot, right? It's that point about which the rotation would occur. And let's say we push on the door with a force like this. The r vector whose magnitude we put in here, we construct by directly connecting that pivot to where the force of interest is being applied. So here's that r vector, right? It goes straight along here. And then that defines theta for us, this angle between r and f. So notice a few things that pop out of this. This torque, or the rotation you get, is maximized when f and r are perpendicular, right? After all, the max value for sine of theta would be 1, and that occurs when theta is 90 degrees. Something else worth noting is that torque is maximized the farther away from the pivot that you exert the force, right? Or said equivalently, the closer to the pivot that you exert the force, the less rotation you get, the weaker the torque would be. And you can see that for yourself, right? I encourage everyone after our session to go play with a door, right? Push on the doorknob, which presumably is pretty far from the hinge of the door, and it'll open or close fairly easily. But if you push near the hinge of the door with the same force, you'll find it doesn't open or close nearly as easily, which is a reflection of what's going on here, right? That smaller R value would lead to a smaller torque, and so you just don't get the same rotation out. But this torque leads to this rotational motion, and that should be reflected in Newton's second law, and we see that for rotation shown here. So notice how similar this is to F net is ma, right? A force caused the change in motion, and the mass was that inertia, or that resistance to the change in motion. We see that here. right? So torque is the action that would cause the rotational motion. The alpha is a rotational acceleration, capturing that change in motion. And I is the inertia here, right? That rotational inertia, which we explore here in a little detail, where we note that it does depend on mass, right? The greater the mass, the greater the rotational inertia. But I also depends on how the mass is distributed. So the farther the mass is away from the axis of rotation, the greater the rotational inertia will be. So we see that with the barbells down below. So if we wanted to rotate both barbell systems, it won't be equally as easy to get the rotation happening. So for this first case, the weights on the barbell are actually pretty far away from the middle, which is our axis of rotation. So a mass distributed far from the axis of rotation, well, that should lead to a greater moment of inertia. But for barbell 2, the weights involved are actually fairly close to the axis of rotation. So if that's the case, then that would lead to a lesser moment of inertia. So same mass, but different resistance to rotational motion, or changes in rotational motion, which is something that I think we would want to know conceptually, right? But I don't feel the technical details on how to calculate I would be all that necessary. All right, that brings us up to about our time together. So thanks everyone for taking the time out of your busy schedules to be with us for this session and the other ones. If you missed those other sessions and would like to see what we covered there, of course, what we did is saved on YouTube, right? So you can take a look at those recordings and check that out. Again, for great resources for prepping, we've got our AP Physics prep book from the Princeton Review. Do check out College Board's website for AP Physics 1. Lots of great information there, including past exams. So thanks again for your time, and of course, best of luck on your upcoming exam.